We ended the discussion of Sub-Riemannian structure of the Heisenberg group, and then we gave a short, quick definition of what Sub-Riemannian manifolds look like in general. So before moving into the group structure on Heisenberg group, I thought we should see an example of a Sub-Riemannian manifold that does not admit a group structure, at least per se is not a group. Let's recall that a Sub-Riemannian manifold is a Riemannian manifold M and G, where G is the inner product on tangent spaces. And we have a distinguished choice of a subspace of the tangent space at every point. And this choice smoothly varies, needs definition. The most important property we want is that this subspace be, this choice of subspaces be bracket generating, which means that maybe delta x is not all of Tx, but the brackets of vectors in delta x and possibly further steps do end up giving us vectors so that the span finally is all of the tangent space. We define the Carnot-Carathédry distance by looking at only those curves whose derivatives lie in this distinguished subspace almost everywhere. Heisenberg group we showed very directly by hands-on calculations that has the connectivity property, and bracket generating condition in general does imply that every 2 points can be connected by horizontal curves despite that restraint on where their velocity must lie. Heisenberg group and more general Carnot groups are examples of Sub-Riemannian manifolds. But we want to see a Sub-Riemannian manifold now that is not a group, namely the Grushin space. The underlying manifold here is R2 with its standard Riemannian structure. That means the inner product is the familiar one. And for choice of delta x, we're looking at the span of these specific vectors, capital X, capital Y. Notice that y has this extra multiplication by x. It's scaled up, at least when you're away from the y-axis. And one noticeable feature here is that unless you're on the y-axis, x and y already span the whole tangent space because they point in perpendicular directions. It's the question of the situation along the y-axis. To check that the delta distribution is bracket generating, I calculated the bracket by applying vectors to a smooth function, and we see that the end result is that bracket of xy is none other than partial y. And that means even along the x-axis, along the y-axis, we have x giving us partial x already. Y doesn't contribute anything, it's zero vector. However, the bracket does provide the missing direction, so span again becomes the full tangent space. So the distribution is bracket generating. We know from Chow's theorem that the space then is connected by horizontal curves. We could also see this directly. First of all, if you are at 2 points on only one side of the y-axis, any Riemannian any curve that lies on this half will be admissible because the tangent space will definitely lie in the span of x and y because it's the full tangent space. So there's no restriction actually on the curves here. Same goes on this side. And for shortest curves, of course, you will take the straight line. If you are on opposite sides, you can again take the straight line going between them. There's only one point where the condition of horizontality is violated, but that's only one point, so therefore it's still an admissible curve. The problem is when you want to travel straight along the y-axis, because then the derivative is not anywhere actually horizontal. It doesn't lie in this span. But connectivity can be met because you can travel a little bit from the first point to somewhere and the same from up there, and then these points you can connect by your favorite curve, even a straight line. So these provide a horizontal curve, and you see that you can make this horizontal perturbation, as small as you want. Therefore, the distance would end up being the same as Euclidean distance. So it turns out that the Carnot-Carathédry distance of 2 points in the space is just the Euclidean distance of them. And maybe it can be an exercise to prove this much more rigorously. The difference with Heisenberg group here is that, for instance, this curve, because of that distance thing, this curve, again, we look at any segment of the y-axis. If parameterized by arc length, say, this becomes a rectifiable curve with either distance, but we see that it's not horizontal. We saw that in the Heisenberg group this wasn't the case. Horizontal and rectifiable class of curves were the same. Another thing here is that in R2 we wouldn't be able to create a distribution that is bracket generating, and at every point we have only one vector. If we had just x on R2 at every point, then bracket of x with x, or any multiple of x, is always 0. So span will never be all of R2. So there is no way you can have one choice of vector in R2 so that it becomes bracket generating. So you cannot have connectivity. And that's why usually sub-Riemannian manifolds we see with constant rank are at least dimension 3. Okay. And because, again, the rank of this distribution is not the same everywhere, this distribution cannot have come from a group structure, cannot have come from a left invariant translation of the distribution at the origin. So, Grushin space, very simple, very nice to play around with. An example of a sub-Riemannian manifold, but not a Lie group. Thanks for watching, and next video will be about the multiplication in the Heisenberg group.